original plan was to bring one from ADD, the Army Research Center. ADD means Agent for Defense Development. And I tried to bring him and talk about this kind of thing. And actually this kind of thing was started by some people in the lab. And here is now he's in the Handong University. And Hwang Iko is still in the ADD. He's a senior researcher there. And they came to us and they tried to do this kind of thing together. And I'm not sure about this kind of thing. I'm not familiar with the terms related to this problem. And I thought that they come to this place and they give a presentation. It's a better idea. But there were some kind of issues because we proposed this kind of project to get some grant, and that one is in the reviewing process. And in that stage, for them coming to this place and giving a presentation is a little bit tricky. So they decided not to come, and also they have some kind of other places to go. And also they don't want to give a I believe there are several reasons, and another reason is, okay, for them, for example, Dr. Huang, he don't want to present English talk. So probably, I don't know. So translation is
guiding systems in language.
So now this is English translation. So my idea was this just simply to convert the English Korean version of the presentation into English version, and then introduce the problem, not the result. We have the result here. We have just some idea of the problem. So presentation of the problem is this. And this is joint project with Won Sang-na, Professor Won Sang-na. He's at Handong University. He's in mechanical engineering and control theory department. What is the issue? Well, what we are talking about is this kind of home-guided missile system. And this one consists of 3 parts. Now, if something is coming and like this one is the target, then the first multifunction radar, this radar system detects target and getting some information from the target. Then probably the information goes to this control center, and the control center will give a command to the launcher. Then the missile will be launched. Then the system consists of 3 parts. The first part is just mid-course guidance. So this one is decided by the initial velocity and the initial position. Then if this one approaches a little bit closer to the target, then there is some sensor here, and this sensor detects the target. Then the seeker lock. Probably it's their terminology. So this one now detected the target. Then the homing guidance started, and this homing guidance is basically related. Is guided by some sensors in here. Then, if this one is close enough, then because of the noise of the sensors, this homing guidance is not invalid if this one is too close because of the noise. Then at that time, some kind of terminal guidance is required to increase the success. So, okay. So this one is consistent with this kind of levels. And yeah. Okay. This one is homing guided collision geometry. So this is a collision triangle. And what is, it's also, the model comes from this kind of picture. And what is this horizontal line? This one is just the initial line of site vector. So initially, suppose initially target was here. Then at time t, okay, now this is the line of site vector. Then this lambda is the angle, and we assume that this is also to make this model valid, this angle should be small enough. Okay. Then, and this one is called the collision triangle. Now if this one, finally. Now here, what is y? Y is the distance perpendicular. Y is the distance between the target and this initial line of site vector. And then this one is PM guiding law. So PM is proportional navigation guidance law is given by this, and this N is called the guidance coefficient. Now this is the okay. Okay, so from the picture page you can see what are these things, and this one psi m is the flight path angle, so this angle psi m. I asked what this one is. Okay, this is nothing. This is just the angle for the missile, but missile does not go this way. Always go some this way. Okay, so we need some kind of control system. They call home guidance loop, and the one is designed in somehow this kind of way. And so A is the acceleration of the T means target. This is the acceleration of the missile, and okay, they are detected, and their effect is computed by this acceleration to integrate twice. Okay, this probably is the notation for the Laplace transformation, and then measure the miss distance. So miss distance means is the gap of the. Okay, this is not the miss. This one is the gap. So measure the error, and then okay. Then if this one compute the distance at the point and find the angle, then somehow from this system, the system is the proportional navigation guidance system. So from here they compute some command acceleration. Then this one is applied to the system, and then always if there is no time dynamic lag, if you command this one and if it is immediately effective, then there is no problem. So then always you can hit the target, but always there is a dynamic lag. And dynamic lag comes from a couple of things. For example, the sensing. If you take the sense, if you sense something and give it to the and this process also takes time. And also after getting some command, the effect of the acceleration comes from will be obtained by changing the angle of the wings or this kind of things. But even if you change the angle, the acceleration, because of some kind of aerodynamics, it takes time to get it effective. So because that kind of thing, there's a dynamic lag. And mathematically, so that they can be modeled using this kind of system. Now, everything matters is just the relative distances. So acceleration target, we may just target is just fixed. It's just a constant. So we remove this, then we obtain this equation, and somehow under the appropriate change of variables, we get this differential equation. Now instead of t, okay, like x, I don't know, they do t go. The time to go is the amount of time to get to intercept the target, and this tau is some coefficient that comes from the time lag, dynamic lag, and so to use this new variable, then this can be changed to this like this. Now this equation is the confluent hypergeometric differential equation of the Kummer time. And okay, to me actually, those people thought that we are very familiar with these things. Okay, that's not true. I wrote this name, this problem first. Okay. Do you have this one in the ordinary differential equation course?
Yeah, I guess so. It's an exam question.
Okay.
So you solved the problem already now.
So for this problem, if n is integer, okay, this one is can be solved using Kummer's base function. If n is not integer, okay, no such kind of solution. So Kummer's method, if n is integer, okay, we can do this. And this navigation coefficient is, if this is n, actually that's the best case, but the actual one is not exactly an integer, right? And n is usually bigger than 3. And for integer case, you have this p and psi, they are the Kummer's base function, and it's given by the gamma function. And then solve this, w is given this, then using w, okay, we can solve the system. And having an explicit solution, having an explicit solution seems very important to them because it saves time, and that one make you to do some real-time computation for the sense of the missile. So missile itself has some kind of small computer chips, and if they can do the computation by itself, and if they guide it, that will help. So they want to do that kind of thing. If n is not a real number, okay, we don't have some kind of things. So okay, so this kind of computation, Jaewon and Min-Soo Go, they did the computation, not me. So they know these things better than me. So they somehow found out what they learned from the numerical modeling course. It's a singular perturbation method. Okay, so someone tried to obtain the singular perturbation method after change of variable. Okay, they have this coefficient tau over Tf. This number is physically about between 0.01 and 0.05. Right? So this is pretty small number. So okay, put this one epsilon, apply this, and then use the perturbation theory. And if second order derivative of y is large, so that is near the target, I guess, then this is this one is not negligible. But if y double prime is small enough, okay, assume this and find the solution. If it's not case, then we need we want success. So y1 should be 0. And then okay, somehow they complete this thing, and using the singular perturbation method, that one looks good. So biased PNG, in that case, more things appears here. And the real number case, there's a singular perturbation. So, okay, so they want to know this kind of technique. Okay, Okay, so that's why we started with this kind of thing. Then, this case, we need the higher order terms also. Yeah, and so this kind of model is just the first order model, and we don't know what should be the second order. So this model. So this model is the first order model of this homing loop, and the second order model probably they have to do something. Now, if you have this kind of analysis for the trajectory, then they can be used in many situations. For example, if you know the trajectory better, and if you can compute the trajectory in a real time, then you can use this one for the terminal guidance. For the terminal guidance method, people they think about this kind of functional, and this functional measures the distance. The distance, of course, we want to make this one be 0, and CF is the weight. Now this one is the size of the, and A is the acceleration, so this one is the total energy you require to make the control. Then differentiate this one with A, then somehow you can find the solution. And if it's weight, you get weight goes to infinity, then acceleration. This is the command. Is this, so somehow this one is bounded. Then you're using this method. So in doing this kind of thing, it's important to find out the trajectory. Then if you can find trajectory, you can do some terminal guidance. Also, they say that it's important to compute time to go. So the amount, the time to arrival to the target. If you can estimate this one correctly, then you can do you can apply some optimization technique to control this kind of guidance. And if you have the trajectory, well, then you can estimate this one better, and using some this kind of classical computation. Unfortunately, still there are some Korean characters here. Now they did some kind of estimate, and having the trajectory analysis using Kumo function or some singular perturbation, the error becomes the smallest. And I don't know. And also, one of the issue is the noise, and because of since there are noise in the sensing process, controlling this noise it becomes important. I don't know what's the signal point between this kind of thing. Probably Professor Hwang, or those people know these things a lot better. So somehow they want to also control the noise in a better way, and to compute the time to go. Better. Okay, that's it. And I'm not expert for this kind of thing. Just I want to show you what are the problems. And if you ask a question, probably I cannot answer. Thank you.